Good evening, all my honors chemistry students. I know you won't be able to understand this or see this, but I'm actually recording this for the second time. I was completely done and didn't have my microphone plugged in. So now I have to do it a second time and replicate it. Of course, it probably won't be as good as the first, but I will do my best. So I hope you're having a little bit better day than I'm having right now at the moment. All right, so we're going to do our first podcast tonight on Chapter 13 on gases, and we're going to take a look at this first section, some properties of gases. Depending upon when you're listening to this, I may have already done some gas demos in class to talk about some of these properties, or you may have already done the Boyle's Law activity. At any rate, we are trying to give you an idea and a picture about these gases. Personally, I think these are some of the ones that are hardest to study because you can't hold on to them, you can't see them. It's really difficult to study gases in terms of liquids and solids. They're visible to our naked eye. So if we take a look at pressure, pressure is something that is around us all around. We have pressure that's forming in our body. You have pressure right now on the outside of your body. And a gas uniformly fills any type of container. You can, whether your container is a room, whether it's a closed vessel like a water bottle, or an open vessel like a bowl or something like that, but there is a gas all around in all these situations. And it's easily compressed. When I see the word compressed, I think about our car tire. If you think about your car tire, you have these four little tires. Draw a little second grade version of a car, and you can see that those four little tires are holding up the weight of the entire vehicle. The vehicle weighs somewhere around 2,000 pounds, and these four little tires are holding it up. Well, if you think about it, that gas, you have way more air that you're pumping into that tire than normally should be in there, and that's creating a lot of pressure. That's why sometimes when you have a flat tire, it can be kind of dangerous. And remember that these gases are mixing all around us. They're not combining to make a compound, they are just mixing around us, and we'll talk about that further in another section. So is there a way that we can measure this pressure? Absolutely. Way back in 1643, Italian, I think his name is Italian chemist, was Torricelli, and he was trying to find a way with glass tubes and mercury to figure out how to measure pressure, and he was successful in doing that. So what you need to understand is that this pressure, he figured out that there's air molecules out here pressing down on this mercury. The more it pressed down, the higher this column would go up, and that would be how he would measure the pressure. Conversely, if you think about being up at Pikes Peak or somewhere with high elevation, the molecules, the number of molecules that you have out here are far, far less. If you've ever looked on the side of like rice-a-roni or some macaroni and cheese packages, it talks about how to cook it in high elevation. The reason for this is there's less gas molecules there. There's less pressure on the water. So there's going to be less pressure here. So this is going to lower this vacuum. It's going to make more air up here. And so the mercury is going to decrease, lowering the pressure. Barometric pressure, you've probably heard if you're a meteorologist and you like to listen to the weather, they talk about the pressure increasing or decreasing. And if it decreases and it's lower pressure, we know that a storm is coming in. Now, air pressure can support 760 millimeters of mercury. You're going to hear that term a lot as we go through this chapter. Now, there's going to be a difference that we talk about a wet gas and a dry gas. The dry gas is what you're breathing in right now. You know that as a dry gas, you should be breathing in 78% nitrogen and 21% oxygen, and the rest is made up of a variety of other gases. Now we're going to do a lab later that we're going to be collecting it over water, collecting gas over water. So that's called a wet gas, and we have to do some conversions for that. So we'll worry about that when we get there. Some pressure units. The SI unit, meaning the metric unit, is traditionally called the Pascal. However, you don't really hear that too much because when we study gas laws, these are the ones that we are mainly going to be taking a look at. That 1 atmosphere equals 760 millimeters of mercury. As we continue on, you can see it in kilopascals. Here's another one right now, PSI. If you have a tire gauge and you're measuring the amount of air that you put into your tire, your bike tire, or your car tire, it's in PSI, pounds per square inch. Our body is feeling 14.7 pounds per square inch. And I know that we're all really buff and strong, and my daughter's probably laughing at me right now about that, but haha, did you hear her? But each of our body, every square inch, we are feeling 14.7 pounds per square inch. So why aren't we just collapsing on the floor? Well, we have air inside of our body too, and that is pushing out with the same pounds per square inch. So we're not feeling the atmospheric pressure. But you can tell that discomfort, like if you are flying or if you're driving over on 95 and you're flying over those hills, you can have some discomfort in your stomach. You might feel it in your ears. That's because we have air in those cavities. And when your ears pop, that's that pressure trying to equalize itself out. So how do we measure that? Gas pressure is a result of collision of gas particles. Later, we're going to talk about the kinetic molecular theory, and we'll talk about more about these collisions. But if you don't have collisions, you don't have pressure. And these collisions are happening between the gas particles, and they're all happening with the walls of the container. And so pressure is equal to force per unit area. And you'll see that in just a couple problems that we're going to do. It's a pretty easy concept though. So let's take a look at our first practice problem, 13.1, on page 446. Now, some of these problems are going to be very easy, and we don't always have to write down everything that's given, but some of these gas law problems can get pretty complicated, so it's a good practice to get into. So it says on a summer day in Breckenridge, Colorado, the atmospheric pressure is 525 millimeters of mercury. What is the air pressure in atmospheres? All right, so for this problem, we are given, here we go, we are given our pressure in 525 millimeters of mercury. And when we do the conversion, that should make sense to you that we are at a high elevation. So we are here in atmospheres, and we know that if we are at sea level, my atmosphere should equal 1. So all I need to do to go from here to here is I need to use my conversion that I circled up here above, that 1 atmosphere equals 760 millimeters of mercury. So I can just simply go ahead and do my conversion. So I have 525 millimeters of mercury. We're getting back to significant figures, no moaning and groaning. So this is going to be 3 significant figures divided by 760. Now that's an exact conversion, so that's going to make that also 3 significant figures in 1 atmosphere. So when I do that, do the division, I'm going to get 0.691 atmospheres. So this goes with our theory. We're in Breckenridge, Colorado. The elevation is far above sea level, so the amount of air pressure is going to be less than you are feeling at sea level, and this conversion shows that. So moving right along, we're going to get to our first law. You may have already done the activity associated with this, otherwise we will be doing it, on Boyle's law. He also was studying this in the early 1600s, that he was trying to describe the relationship between pressure and volume, and he found out that it's an inverse relationship. So from your math class, inverse should make sense to you that if pressure goes up, the volume's going to go down, or vice versa. So in our activity, you probably got this nice little graph like this that is going down, proving Boyle's law that this is an indeed inverse relationship. All right, so if I go ahead and I take a look at my pressure, excuse, the phone was ringing there, 1 over the volume. So it's pressure times 1 over the volume is also going to prove Boyle's law. Because if this is a indirect relationship, inverse relationship, pressure times volume is equal to a constant, then if I graph pressure of 1 over the volume, that should also be a direct relationship. So again, these are just going back and forth to make sure that we are proving Boyle's law. So we are assuming, what are we assuming here? We are assuming constant temperature and the number of particles. Well, when we were in our classroom, the temperature in there was pretty constant, and the number of particles in the syringe, if you remember the lab, was also held constant. We didn't add any new air in there. So we could study Boyle's law. So the product of pressure times volume is a constant, and there isn't anything trick to this formula at all. The only thing you need to keep in mind is that you have to make sure that the units are the same on both sides, meaning that if pressure is in millimeters of mercury, this one better be in millimeters of mercury, and vice versa. And so if this is in milliliters, this has to also be in milliliters. Okay, so let's take a look at our first example here. And again, like I said, we don't necessarily have to write down all the variables for this because this is a pretty straightforward formula. However, I would say that it's a good practice to get into. Now, the only trick in reading these is to make sure that you're in the same condition. So I have a volume of gas that has 53.2 milliliters at a pressure of 785. So these are in the same condition. Then all of this gas is transferred to a new vessel with a pressure of 700 millimeters of mercury, and what is the volume of the new vessel? So my pressure is going to be 785 millimeters of mercury, and my volume is going to be 53.2 milliliters. It's a nice 2 there, sorry about that. And we have a new pressure that it tells us is 700, 3 sig fakes, millimeters of mercury, and it's asking us what the new volume is going to be. So we know what Boyle's law is. We know that it's pressure 1 times volume 1 equals pressure 2 times volume 2. And as I substitute my pressure 1 in, I have 785 millimeters of mercury times volume 1, which is, wow, 53.2. That's a nice number I got over there. And that's going to be in milliliters, equals 700 millimeters of mercury times X, which is our new volume. So all you need to do is divide by 700 on both sides, and I will get my new volume. A little bit of algebra here. And my new volume is, oh, there goes the phone again. My new volume, where's the answer? 59, Sam, can you grab that? 59.7 milliliters. And you should see that here my pressure is decreasing, my volume should increase, and that's exactly what happened. And that's also proving Boyle's law again. So my practice problem here for you, I'd like you to try it. It's on 13.2, page 449. If you get an answer that your volume is equal to 1.22 liters, you have done this correctly. All right. So I know this probably isn't the best because that was day 2, the second time of doing this one. I hope you guys had a great night, and I will see you soon.